up the PowerPoints we were looking at the other night. So let's go ahead and look at those. I thought I had them loaded up. You go, and this is even new. This is even on the new programming software, the Ars Logic 5000 or the Studio 5000. So what happens when you install the software on your computer? You'll end up with a Rockwell. You'll end up with a Rockwell Automation folder in your list of programs. And so they're Allen Bradley PLCs, but it's run by Rockwell Automation. And when we click on that, we should see something called RSLinx. And this is where, and then RSLinx Classic. So this is still what you use to connect to the PLC. What's a driver? Or hardware. So, well, it could be internal too. So everything. So basically, everything runs on the programs. All your computer can do is run programs. All your cell phone can do is run programs. It's a computer too. Our cell phones have more processing power than the first computers that I actually worked on. So it's really, really amazing how the advancement that we go through. I need to go through the whole thing. So we're using an interface. Like I said, you can look on the side of the PLC. I'm using this DIN connector. I think it's I can't remember how many pins. This works off of the what we call RS-232. It used to be EIA, was the Electronic Industrial Association, but they disbanded. It was a certification group, and they turned this over to the Telecommunication Industry Association. So a lot of times you'll see it EIA or TIA/EIA. It's called it was called RS-232C, which is the version we're on. And a lot of your certification companies, that's what they'll do. They'll give it a letter to start off with, and then they'll give it a number. So the RS-232 was just the number the EIA was on when they set up this communication protocol. This guy, it's a serial protocol. This was used for years. In fact, if you get into an old computer where you actually plug the mouse into a DIN connector, a little round connector, that's RS-232. It's just a IBM. IBM went from the DB9, which is this guy right here. So this is the DB9, and why it's called a DB9 is that it's in the shape of a D. And the female is got a metal, and it's in the shape of a D, and the male's comes out with a shell in the shape of the D, so you can't plug it in backwards. So it's one of those connectors that's pretty much, well, what we call mercy-proof. So this is RS-232. Well, the problem is that the RS-232 port is not available on computers anymore. What dominates everything now is Universal Serial Bus. So, but we can still get the older interfaces by buying these things we call dongles. So this is a dongle, and what it does is it takes USB, which this is what we call a B connector. A standard B. This is the first one they used on USB. Now they've gone all over the place. They got a sub-micro D now that's a B that's out there. And then of course it converts over to all the pins and everything for the ORS-232 interface. In fact, the parallel port, the EIA 1284 port, the old big parallel port. I don't know if you know that. We used to love that. We ran it with a print. It was a printer, but you could address that thing. So we would hook up all kind of stuff to that port and play around with them and access it through our own program. So the first thing I had to do is when I came to RSLinx, first of all I had to install this, and of course it didn't work because my operating system didn't have a WAD for it. Starts with a D. D-R-S-L-I-N-X. So a driver is software. It's a machine language program that's specifically designed to run hardware. Everything's got a driver. In the operating system that controls the computer and allows you to use what we call the shell, is thousands of drivers, but it can't have all of them. So what that means is, a lot of times when you plug a USB port, USB's got, especially one that's got memory in it, it'll automatically install the driver for you. And I know y'all seen that before. You plug a new memory stick on there, the little gray box will pop up down at the bottom, saying installing the software. What is it doing? It's installing the driver. So you can make that work. This one doesn't have that, so we got it. We have a CD. In fact, I left it in some of these computers, a little tiny mini CD that had the driver on it. So the first thing I had to do, we go into, I think did I show you all Device Manager? Device Manager is, shows you all the hardware that is being controlled by your operating system. So what happens when you plug this in? I wish I didn't have this up here. What you'll do is you'll get a category that says Other. And if you ever see that category in Device Manager, it means it knows something's there, but it does not have the driver. So that popped up there. And of course, what you do is you'd come in here and just click on it. So I'm sorry. COM ports, so when you look at your computer, you won't have any COM ports. And what's very important is that this guy right here is at COM7. So what I had to do, it came up Other. I had to right click on it, go to Properties, and then I went to Driver, and I did an Update Driver, and then I pointed it to the DVD. Then after that, it worked. So sometimes everything you got does not have a driver. It'll come with a DVD or a CD that you have to. So what it does is it assigns it a number. So when I come up here and want to communicate with the PLC, so I'm going to bring up RS Link, if I didn't close it. Don't look like I did. Looks like I did. Oh, I didn't get that far. So Device Manager. So this is everything. And one thing you need to look for, if you got a category called Other. So if you got a category in there called Other, it means whatever's in that category is not working. And sometimes you can click on it and it'll say, look online. And a lot of times you can click on that and it'll go out on the web, on the internet and find the driver for you. If you don't, odds are you got a DS. So this is everything. So you can come in and look at the resources and all that other stuff. That's called Device Manager. So you can get it from there, or you can get it through Control Panel. Control Panel is harder to find on Windows 10. Control Panel is like, the other day, I think I was in your class and y'all didn't hear, I couldn't hear y'all. Well, the problem is I had to come into Control Panel where y'all couldn't see what I was doing, and I had to switch over to my headset because it was choosing the wrong thing. So this is where you can go in. So you can set up different sounds that you want it to play. It's pretty neat. So you can also go down to System, and this is true on Windows 10, and you can access Device Manager here too. So Control Panel, that's a very, very important. You can go in and configure some of your applications that you have running on your computer. So I keep a shortcut even on Windows 10. So what we do is once we do this, so I install my driver. Then what we have to do is we have to install the driver into RS Logic. So wrong place here. So I'm gonna go over here, go to Programs, Rockwell Automation, and then RS Links. This is the program that we use to install the drivers into RS Logic 500, into the application. So we go to Comms, and then we go to Configure Driver, and then this is the list of drivers that this guy here's for. So right now we're running, I don't know why this is in there. Ethernet IP is running, so I don't need that right now, so I'm going to stop it. I don't know what this guy is. And so this is the, this is the 480, this is the 480, the 485 driver, and it's running on COM7. But sometimes it don't do that, so what you'd have to do is configure, and sorry, wrong one. So I can configure, and then you would have to select what COM port that it assigns it. Does that make sense? So you got this little scroll button right here, and you could go in and find that COM port that shows in Device Manager. So Device Manager shows that, and you can find that. And then that's all you have to do. Then you can come down here and hit Auto Configure, and it'll go up there and set everything up for you. But it's got to be on the right COM port. If you have it on the wrong COM port, it'll come up and say, I can't find anything out there. So what you do is go in Device Manager, hit on COM ports, and see which one is your computer has assigned to it. So those are all what we call PNP devices. And sometimes it'll come up and say you got a COM port conflict. If it says that, then you got to go into you can go into Device Manager and change over to another COM port. So you can do that kind of stuff, which is pretty. So once I do that, I'm gonna click on this little guy right here we got several ways to do it. And this will show me what's out there. So this is the driver we're using, this DFI 485, and I click on that, and it tells me I've got this PLC out there. So now I'm communicating with my PLC. So it went out there, once I set all that stuff up, it went up. So setting up drivers are not easy. If you're doing Ethernet, you have to assign it an IP. You have to assign it an IP address, which is a lot different. We'll have to show you that in another class. So first thing we do is we establish the communication. So all y'all should be set up. So we've got a shortcut down on your taskbar. It's a ladder down there. And this is the programming logic. So y'all go ahead and find that. Well, first of all, connect up your USB cable. Get the computer that's on the number that's on the PLC. I think yours is 2. Connect it to the one closest to you on the left-hand side. On your left. The one closest to the front. Closest to the front. All the way to the front. Yeah. Because the problem is, if you plug it into the wrong one, it might do what? It might assign you another COM address, and then you can't find it. So once you do that, what you can do is down here on your taskbar, we've there's a ladder down there. Y'all see it? Okay. Just double click on that, and this is RS Logic 500. And this is what I was showing y'all a little bit the other night. So once we get in here, the first thing we would do is up here on the ribbon, top ribbon, it's got something labeled COM. Now plug that in, the one on the left, closest to you. Your other left. Now this is where, if you had a bunch of PLCs networked together and your computer you could do it with one computer. So the first thing we have to do is find our PLC inside this COM. So if you click on that and just go say system COM, you'll see that's the first listed. Go there yet? You'll see mine? So we click on that, and what would happen is all the PLCs that's connected to the network would be displayed. So we're using the Allen Bradley DFI1 DH485, and so you click on that, and you should see a MicroLogic 1000 or 1100 PLC. I'll wait for y'all to get caught up. still booting. Huh? What over? No, we're not supposed to have that. So what's happened, well, once you select this, so what we just done, what we just did was now we've got communication with our PLC, which means we can program it and we can download it. We still got a couple of little steps we need to go through. So let's hold up right there. Let me go into the PowerPoint. So the first thing you have to do with a PLC, number one, is establish communication with a PLC. I don't care. And the problem we have is that these big companies like Siemens and Allen Bradley, that the same software or the same programming application programs several PLCs. Some of them use Ethernet, some of them use Profibus, some of them use different types of ways that they can interface their computer. So that's why you have to install the driver. The Siemens 1214 that you'll deal with if you take the PLC3 or the ILC 212. It's got Ethernet, and that's all it does. So it's a lot easier to set up, because that's the only thing it supports. So docs, let's see, ILT, program controller, PowerPoint. So we were working inside chapter 6. I can't remember exactly how far we went. I know we got through, showed y'all the programming languages, got through with the different rules for programming PLC. So there's 10 of those. And then we looked at the symbols, right? I'll show y'all how to do symbols. We talked about that in this class, right? And we talked about comments, the yellow, showed y'all where you can put comments in there. Then we looked at this. This is actually out of the program that's running the Festo line. So the Festo line, it's running RS Logic 1500 PLC. So we'll go back there and actually look at that. And so in PLC3, what we do is we convert Allen Bradley programs over to Siemens programs, which is pretty good. PLC. If not already accomplished, establish communication with the PLC, start a new program project, select the model of the CPU, configure the I/O, which we haven't talked about. I'll show y'all what you do that at. So right now, these are modular PLCs, but they're what I call hybrid, which means they come with a few internal input ports and a few internal output ports. Then on the right hand side, we could add up to 5 modules onto this PLC, which makes it a modular PLC. So right there, there's a little door, you can see it square that you pop off on the right hand side, and that's where on this DIN rail, this top head DIN rail, you snap them on there, or just in the backplane now on these PLCs actually runs through the PLC. So on that rack mount that we looked at, it had connectors in the slot where you plug them in, but on these, the actual backplane runs through the PLCs and it runs through the module, which is pretty neat. So programming application, we need to make sure our PLC is offline. I mean, not our programming application is offline. So yours is probably on this. This should be on this side over here. For some reason, mine got over here. So I think, let's see if I can let me move it. Yes. So yours is on the left-hand side. So by default, it starts up in the offline mode. So that means we can create a program. If you click on the little scroll button on the left, you see I can go online. Well, right now I can upload, which means bring a program that's in the PLC into my computer. Or right now we can't download because we haven't created a program. We okay? So this is where this is where the PLC ladder diagrams are created or modified. So what you'll have to do is, and we do this a lot, because we'll write the program, we'll upload it, and something's not quite right. Well, your program is still sitting right there in front of you while you're writing and you're connected to the PLC. So all you have to do is just do what? Go offline, make your modification, re-download it again. And like I said, your application will check for syntax errors, but if you got it in the right syntax, it's not gonna find those things. If you plan to download the program to the PLC, by the way, if you're offline, you can create a program without being connected to the PLC. So a lot of people do that. They'll be at home and they'll write their program, and then they'll come in and plug into it. Y'all can't do that, by the way, because y'all don't have these computers with the application. No, we downloaded the PLC. That you got it. Yeah, I know, but that's the problem. We're used when we download, we're used to getting something from the internet and bringing it to our computer. In PLCs, it's different because this is a computer too. So this is the PLC thinks it's the big boy in the house. So we download, so we're acting like the internet. Where the internet, you're downloading from the internet. Well, what we're doing, this is the guy right here. So we download into this PLC. So sending the information from the PLC, from your application in the PLC is a download. To get information to get the program that's currently in your PLC into your application, that's an upload. So it's basically opposite of what we do on the internet, right? And like I said, because you're hitting some type of data communication equipment, you're not connected to a computer, you're connected to some type of data communication equipment, and you're downloading through that to your computer. Place the RS logic in the offline mode. So right now we got two modes. We got offline and upload. That's the only two things we got. But like I said, when we're programming, we'll be switching between online and offline. To modify the program, you can't modify the program while you're online with the PLC. And you can't download into the PLC, so you got me thinking. You can't download into the PLC unless it is in the program mode. And I can show y'all how you can switch it. So the PLC's got three modes we can operate in. We can operate it in the run mode. So when you switch it to the run mode, you can't put anything there. It's running your program. We can put it in the program mode. The program mode is where we can upload or download programs. And then on all these new PLCs, we have what we call the remote mode, which is what ours is. Remote means your application switches the PLC between those other two modes. So right now we're in the remote mode. So when I try to download a program, it'll automatically say, are you sure you want to download it? And it'll switch it into the what? Switch it into program mode for you. And then it'll come back and say, okay, do you want to go back online? And you say yes. And it goes into what we call online mode. Create the new program, select the correct CPU for the PLC being programmed. All ours, this information is on the right-hand side of just about every PLC. This is a MicroLogic 1100, and it's a revision B. You should see a revision B up there if you look at the right-hand side. In every PLC I've had. But what happens if you put a module on here? You lose that, right? So, and that's the way you gotta have that information, guys. So you better write it down if you got all the same PLCs in your company, you got no problem. But if you got all these different models of Allen Bradley PLCs and you don't know what the model is, then you need to write that down, right? Select the correct CPU being programmed, insert a rung before the end, insert instructions into the created rung, and add as many rungs as you need to do that. So we come up here. So let me exit this. Get back here. So we've already established communication with the PLC, right? So what we do is we'll come over here. You got two options. You can click on File and you click on New, or you can click on the little it says new right here. By the way, on these, on your taskbar, on your ribbon, if you hover over an icon, it's going to tell you what it does. So open means I can load a previously stored program out there. So I'm going to click on this one that says new, and the first thing it's going to do, every PLC you program, the first thing it's going to do is ask you what model are you trying to program. So what this does, it brings in the right instructions, the right machine language into the compiler, and it also knows exactly what instructions that PLC has. So what we'll do is we'll scroll down and find MicroLogic 1100 Revision B. Y'all doing this? Go ahead. So MicroLogic 1100 Revision B. And then we can come up here and hit OK. And it brings up our program application. Everybody done that? See there? $1,100 Revision B. Series B. On the thing it says Revision B, which is kind of confusing. Now on the left, we have what we call the project tree. We can come in here and we'll look at some of these later on inside that. No, 1100. MicroLogic 1100 Series B. So we're ready to start writing our program. It's going to put the end instruction in there automatically. And anytime it hits the end, it tells it it's a loop to go back to the first row. So what we're doing is we're programming ladder. RSLogic 500 only supports ladder. And what you're going to find out that there's probably a 99% chance where you go to work at if there's going to be ladder. This is what guys here in the United States use. I'm not saying it's not going to be that language. And the other language, once you learn one language, it makes it easier to learn other computer languages. So I started off with machine language, then I moved up to basic, then I Visual Basic, played around with C for a while, but you find, once you learn the logic of programming, it makes it easier to learn other languages. And this one right here is fairly simple. I mean,
last night we were working right there. How does this tie into that? Like, is that code like one of the things you're trying to do something?
Well, we would connect to the PLC, and then we would run a programming application called, we use the S7 for those. And it's a programming application that programs it. Programming, it would be like your brain programming your sensors. Your brain don't program your sensors. Your brain processes information from your sensors. So sensors are providing inputs to the PLC. It comes into a program, and the program makes a logical decision on what it needs to do with that information. So that's it. That's what it is. A lot of people say it's the brain, but we are, God programmed our brains, right? You understand that? You're writing the program for this one. So what you're seeing over there is you're seeing a program that some human wrote. I heard somebody else say, man, this is neat. Well, and what's so nice is you look at them and all of them look exactly the same. So what's different but the modules are not the same. So what's different between them? It's the program that's written. And so that's what we're doing. We're learning how to write the program and the syntax for writing the program. Now, luckily, just about all compilers will check for syntax, and syntax is the correct way of writing in a language, right? So when you take English Comp, if you take English Comp 101, that's one of the things they'll grade, not only your content, but they're going to grade your syntax. So syntax would be what? Correct spelling, using the correct, thank goodness for Grammarly. Yeah, anybody use Grammarly? So that's what that is. A Grammarly is a what? It's a syntax checker for you. It does a really good job. So what we're doing is we're writing programs, but we're going to write it in a language called, so even though this guy has no idea, this guy right here has no idea what ladder logic is. It runs machine language. That's the language it runs, all it knows. But what these guys do is they allow us to write these high-level language programs in a language that we understand. And then when we send it to it or download it, it compiles it and automatically converts it into machine language for the PLC. So yeah, if you looked inside that memory, all you see is ones and zeros. We used to have a program called Debug, which is really cool. They took it out with Windows 7 because it was dangerous. And we could literally dump the memory of the machine and see all the ones and zeros. Of course, it didn't do it in binary. It did it in hex. It displayed it in hexadecimal for us. But you could literally dump the memory of the machine, and you could write into it. Back when we had floppy disks, there was a section on the floppy disk that actually had all the errors that it would display if you did something crazy. And we figured out how to break into that, and we rewrote all these error messages. So every time they formatted the disk on this computer, they'd get all these new error messages. So on the left, and we'll look at this. These are the project tree. Now, the older versions of the PLC program of the languages took a lot of the control away from the user because the original people, the program PLCs, were electricians. So what these guys do, or what RS Logic 500 does, is it manages the memory in the PLC for you. So what we have over here is we have all these files over here called data files, where certain information is kept for you. And then you don't have to worry about it. Now you can add more, and we'll show you how to do that later on. This is not a fixed PLC. I'll try to boot up a 1000, and this over here will look a lot different because everything that's in it you can't add anymore to it. This one, though, we can add more data files. So we have input information, output information is held in file 0. Input information is held in file 1. Status information is in file 2. Binary information, which is really cool, we'll talk about this, is in file 3. Timer information is in timer 4. Counters in timer 5. Control, we won't talk about this. If you take PLC2, we'll talk about the control register. N7, this is integers, so this is where all your integer numbers are kept in there. And then floating point numbers, these are real numbers. These are the numbers that deal with fractions. So we'll deal with this. This will deal with automatically. Integers will deal with even when we get into counters and timers. So we'll deal with R6. N7 and F8 when in PLC2, if you take that back. So we'll get down through all of them until we get down into R6, N7, and F8. And we can add more, by the way. We'll show you how to do that later on. Each one of those handles 256 entries. There might not be, and that's at least 256 words of memory. I'm going to come over and just click on the input, and this shows me the states of my inputs right now. So, of course, this is what we call the input data register. So when the PLC reads the inputs, it don't go directly into the program. It goes into this guy right here. And notice this is set up in words. We did talk about words, bytes. Did we talk about bits? Right, nibbles. Yeah. In this class, though, y'all, we talked about bits, right? Nibbles, bytes, words, double words. So what they've done is they've given these groups. I'm pretty sure too, but it's something we need to know because we'll talk about this a lot, and we need to understand this. Any PLC or computer programming that you go into. So what they've done is we know that we know the each individual digit in a binary number is referred to as a bit. So what they've done is they've came up here and set up groups that we're going to deal with. And I don't know how many I've got up here, but we'll see. So each one of these would be referred to as a bit. Groups of fours, starting from the least significant bit, this is referred to as a nibble. Oh yeah, I mean, it's a binary number, so I could have come up and did this. Put a one way out here. This first bits right here would be a nibble. That would be the first nibble. So it's just a group of bits, whether they're ones or zeros. It don't make any difference. Groups of four is called a nibble. Groups of eight, which y'all probably heard, but it's been dropped here lately. I hate it when I hear the term gigs. I got 8 gigs of memory. Well, it's actually gigabytes. So a group of 8, no matter what ones or zeros, 1, 2, 3, 4, 5, 6, 7, 8. A group of 8 is referred to as a byte. And memory is laid out in groups of 8. Whether it's a 64-bit memory processor, every address of memory is made up of 8 bits. And so when they say I've got 8 gigs of memory, it's actually 8 gigabytes. A group of 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. A group of 16, we know whoever started doing this is not hungry anymore. We refer to this as a word. A group of 32 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think I missed one. Let's go over it. 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 31, 32. This has 2 names. In computers, they refer to this as a double word. In PLCs, they refer to this as a long word. So if you're talking about this computer, they'd say, okay, if you looked in what we call the registry, which is really, y'all need to stay away from the registry, you can mess your computer up. But that's where it stores all this information about what it needs to do with all these different files that come in. So it's basically the configuration, how to configure the operating system when you load in a certain application. They would call it a double word. PLCs refer to this as a long word. A group of 64 bits in computers is called a quad word. PLCs refer to it as a double long word. A word is 16. No, 16 bits. Yeah, nibble's 4. So it looks like they were hungry when they started this off, right? Nibble, bit, nibble, byte.
And they went all the way over the word. They should have kept it.
Yeah, they should have kept it on the food market, right? But then they.
What do you call that though? Supper or?
Yeah, I don't know. So we're okay. So Alan Bradley deals with words. Siemens deals with bytes, and that's one of the big difference when we get into a Siemens PLC, because we get used to dealing with these 16-bit storage locations, and then we get into the Siemens, and they go back to bytes. But you can still go bytes. You can still access information in bytes, words, double words, and long words and double long words. I'm glad we went back over there. So when you look at each one of these storage locations inside a data file, they're going to be in groups of 16. And then we can put 256 entries in each one of the data files. So if you've got inputs, think about your inputs. Each input requires 1 bit, and you got 256 words to work with. That's a lot of inputs, guys. And you can build one if you got enough memory inside your computer. So we need to make sure we understand the PLCs. We look at this, look at that. So this could give us a problem, and we'll probably wire this up. The problem we have with this guy right here is he'll come over here for some reason. And so when we connect the PLC, so let's say an input. So the PLC has got a common. So if you look at, if you look at the inputs across the top, you'll see DC common. Y'all look at the top of the PLC. We have 2 DC commons. So what we can do on this PLC, we got 2 groups that we can set up as sync or source. And we're setting our inputs up syncing, so that means my input devices has to be sourced. So we're taking that common. So this is a big problem we have with the lab, and we're coming over and we're hooking our DC source up like this. Oops. Okay. And then this runs down and all the inputs come over here and connect right here. And then we come over and let's say this guy's got this symbol right here. So that means what that means is I'm going to come over here and it says I'm going to put one of these. But that's not exactly correct. Because when we're dealing with inputs, that is not, even though people that's been in the field, they understand this, the difference between a software instruction and a physical instruction. So what happens is this, when we're dealing with inputs, is what we call an examine if open. So if I use one of these push buttons, would that be false or would it be true? It says it's true if it's open.
Okay, not true. Not open.
Yeah, so it'd be false. So this guy, though, he'll do this. He'll put a normally closed push button up here, and in the program, he'll use an examine if open instruction. That's wrong. So what I should use here is I should use one of these. This is examine if closed. We want it to be true because it's a normally closed push button. We want it to be true, right? You understand that? So this is the one we would use in our program. So if he's using a normally closed push button and he's using this instruction right here, then that will start off false. So when I'm dealing with contacts that are not from an input, then normally closed, normally open is perfect. But when I'm dealing with actually true inputs, then this is going to cause a problem. And the big problem is if I come over here like this, so this is a standard, this is probably the most used circuit out there. I'm going to start off with this right here, and I'm going to label this stop. And I'm going to come over here, and I'm going to have a normally open, and label this start. And then I'm going to come over here, and this is not program controllers. This is relay logic. And I'm going to label this run. And I'm going to come over here and put a contact right here. I'm going to label this run. I didn't do that good job. People call this a memory circuit. They'll call it a ceiling circuit. It's called a 3-wire circuit because it gets 3-wire numbers. So what happens is I come over here and press the start button. As soon as I press that, the run coil energizes, and it would come over here and close this contact right here. And now it seals itself in. Now I can let go of the start button. This is all over the place. I mean, this is all over the place. We got an example over here on the amateur line. Okay. So, huh? Yeah, it could be, but it's a normally closed. If it's a normally closed push button, I would have to put it over here and turn it like that all the time. But if he comes over here and programs this, and he uses one of these instructions. So he's writing the program, and this is the way this guy right here writes it. I'm trying to get to my marker, guys. So I got. So this is the way he would draw this program, and he does it several times. So he'll use examine if open, then he'll come over here, he'll use an examine if closed, then he'll come over here and he'll put an output coil. Let's say output 0 / wrong PLC, guys. The way this guy here addresses, it would address it. So I'm teaching Siemens this semester too. So it would go output. That's not the number O. I mean, it's not the number 0. It's an O. If somebody's gonna mess up this semester, then I'm gonna put a colon, and then I'm gonna say 0/0. So this will be internal because we don't have any slots. So internals on this PLC starts off on zeros. The Siemens PLCs, we can set them wherever we want to. Okay. So let's put this program in there the way this guy would put it in. Okay. I'm gonna discard this. I shouldn't close it. So let's show you how to put it in. So here's our program. I'm gonna close this out. First thing we're gonna do is insert a rung. So I'm gonna come up here and click left on that, and it should turn. I'm gonna left click on that. By the way, we got mice. Anybody need a mouse? When I click on that, we're going to, right now, your user up here has probably got a lot less than mine's got in there. Like I said, I'll show you later on how to add that. But this right here, this is, if you hover, if you don't know what it does, just put your mouse over it and it'll come over and what does it say? It says new rung. So I'm going to just grab that and just pull it down. And notice it becomes rung 0. So on Allen Bradley, the first rung is always rung 0. And of course it gives us an error because I've got, this would be an electrical short, right? Understand? So I'm going to come up here and I'm going to pull down this examine. So if we hover over that, it should come up here and say examine if open. But that's the wrong one. Okay. And then I'm going to come up here and I'm going to pull down and examine if closed. This right here, this is your drop down or your branch. I'm going to pull this down. Now notice where you can insert it turns green. Y'all see that? By the way, you can drag. Everybody knows how to drag with a mouse, right? So I can put it on either side, and then what I'm going to do is I'm going to come up here and grab this. Don't click here to move it. Come down here to the corner, and then I can drag it inside there like that. Are we okay? Yeah, and we're going to see why this right here is wrong. And so what we're going to do is we could do this on the fly. So let me come back. Nobody do anything because we're going to show you several. By the way, you can delete anything by just highlighting and then hitting the delete key on your keyboard. Everybody knows what your delete is, right? Y'all gonna be using that. So if I come down here, I'm gonna pull this down, and I'm gonna come up here, and I'm gonna enter an address. So we're gonna assign this to switch 0 on our trainer. So I'm gonna say I for input, then I'm gonna put colon, Rich, and then what comes next is the slot number. Well, if they're internal, these are gonna be 0, so I'm gonna put 0 and then /0. So I just assigned that symbol inside the software program to this first switch on the top left hand side of your train. And then I'm going to hit enter. Well, when I do this, another box pops up. I'm going to show y'all in a minute how you can come back if you accidentally move over, how you can add this stuff. And it's asking for a symbol. This is up here, this is where you'd enter a comment. Y'all don't have to do this. I can spell comment. This is going to be required. This symbol is going to be required. Okay, I'm going to come up here and type in stop. This is going to be supposedly going to be my stop button. And then I hit OK. So notice my comment did what? Went to the top and my symbol went in green. Symbols are required. Or we could do it this way. I can pull this down, pull down the down drop. Then what I want to do, grab the symbol down toward the bottom, because if you grab it up here, it wants you to change things. Drag it into there. We okay? I'm going to put another contact right here, and then I'm going to put a symbol for a pole right there. Everybody okay? Yeah, so it's a run branch. So we stood right here. So first of all, I put you got several options. You can put the run branch down there first. Okay, so you just drag them down, right? Okay. And then you could bring the contact in here. It's examine if open. What we're doing is we're doing the circuit that I just drawn. So this circuit right here, let me draw this up here and then so this is the circuit that we're doing. We're going to call this guy here run. So we'll call this guy right here. No, we'll call it start. We'll call it run. We'll call it stop. We'll call it start. And this contact right here is going to be controlled by that guy. But this is not going to work. But this guy does this all through this textbook, where he'll have a push button labeled stop. He'll draw it as a normally closed push button, and then he uses an examine if open instruction. Okay, so we're going to drag another contact. Are we okay?
Yeah, I'm trying to figure out. So, yeah, in the beginning, where it says the comment stop, and just open and close, can you explain like what's going on here?
Well, nothing's going on right now. We're drawing our circuit, and we haven't run anything. So what we're doing is we're drawing the circuit. And then we're going to run the program, and we're going to come over here and flip these switches over here, and we're going to see what happens. To clear, all you have to do, guys, all you have to do to clear is just highlight it. If you don't want it, if you make a mistake, just click on it and highlight it and hit this world famous delete key on your computer. So we're going to be using that a lot. So we'll start from the front again. We okay? So don't go back to the front if you're past this. No, you're on the side down. Don't click like that. So, yeah. Probably, that page, other circuit, copy, so, so you can pull this branch down anytime you want to. So you can pull it down later and drag stuff into it. So like I said, we got mice up here somewhere. If y'all want to use those, we'd have to find them. So we got two. What I'm gonna do now is I'm just gonna draw the circuit, and then I'm gonna come back and fill in everything. So if you hit enter, you can go ahead and do the symbol, and I'm gonna show you how we can actually set up a symbol thing. So I can literally come down here where it says address and symbol, and I'll show you how to do that later. You can go ahead and do all your symbols before you even start. And then once you get a symbol, you can use a symbol instead of the address, right? So I'm gonna click on the question mark, double click on it, sorry, and go back. So input, colon, 0/0. So I've just assigned that symbol. Of course, it pulled it up. I could have put the stop because it was in my symbol table. I've just assigned that symbol to input 0 over here on your PLC. Then I'm gonna come up here, double click on this one. I'm gonna assign this to input 0/1. Now I want to. I've screwed up. But I want to assign a symbol to that. Well, when you right click on it, it says right here. It says edit symbol, and now I can call it run. So even if you don't hit enter, you can always come back and do it. Oh no, I didn't want to do that. I messed up. Hold on. So I'm gonna call it start. Because I want to call this guy over here run. I'm going to assign this to output, colon 0/0. So this output on your trainer, right here, I've assigned this to that.
Wait, why is it 0/0? Okay.
We have to identify the portions of the command. So we have, and we'll look at the actual addressing scheme. We're taking things, that, so what I've done is I've assigned this over here to the data. So inputs are actually file 1. Right now we're not having to do that because the inputs are internal. So that means that if you say I, it knows to use file 1. So I could come up here and so the actual syntax would be input file 1 colon, and then we have to supply a slot number, right? Okay. Well, it's not in a slot; it's internal. The CPU doesn't have, so on a rack-mounted CPU, a rack-mounted PLC, the CPU's in slot 0. But the CPU don't require a slot because it's what? Yeah. So we still call it a slot number, even though technically it's not a slot. And then we got all these bits in there, and we have to specify bits. So I'm saying, okay, these are internal, and I'm going to deal with this 0. So what I've done, down there on your PLC, you have a switch labeled what? 0. So what I've done is I've connected that symbol to that switch. Okay. Now down here, what I'm going to do is I'm just going to type in run, because I've already assigned it a symbol. So what's gonna happen is when this output goes true, this internal contact that's not even real, it's a program, is gonna close. Okay, so what we're gonna do, right now it's saying I got an error. That's what all these E's over here. What I don't like about RS Logic 500 is it keeps the errors out there even if the run's good. So right up here, we got this thing that looks like a computer screen that says verify project. We're gonna click on that and notice the errors go away. That means my program's in the right syntax. So we're okay. Everybody okay? Everybody okay? Anybody need help?
You put run at the end, mine's turning black, how do I make it turn green like yours?
Just click away from it.
Zero.
0/0.
0, that's why they basically tell me on, one is like, it says on, and that's why I said, open on the second one, right?
Yeah, because according to this guy, when he, in this, what we're doing is I'm trying to show y'all why this right here is wrong.
Okay.
So we're not doing this program, we're doing the program that's most widely used out there. We call it a start-stop station. So anybody need help? Well, let me bring my program back up. Sorry. Now, once you call this output run, what we're doing is this is a simulated core. It's not a real core, guys. It's a simulated. But when that goes through, this output right here is going to turn on. And what should happen is your E should disappear. Huh? Right here. Right here. See a little computer screen. If you go up there and hover, it says verify project. Just click on it. And it should come up clean. Everybody come up clean? Everybody okay? Everybody okay? Okay. So what we're gonna do is so we got our PLC in remote, which means we'll be able to switch it between. We'll bring it down to program automatically. So right up here, up through this, click on the little scroll button and go to download. What's that? Yeah, this is the part number for the PLC. So did you select 1100 PLC? One thing that I don't like about RS Logic 500 is that have we assigned this thing a name yet? Okay. So, according to my diagram, this switch right here should be a normal close switch. So that means I should be able to take switch 0 and push it to the left. And what happens to your diagram? It went what? The right. It's not green anymore. So when I hit switch 1, switch 1's supposed to be momentary. We're just supposed to touch it. So what's my problem? So if I use a normally open, if I leave it open, put it in center position, input 1 goes true, and I'm just going to come over here and touch. I mean input 0. Just touch it. and it seals itself in. Now the problem is a stop button is supposed to be a normally closed switch. We're using a normally open switch. So what would happen if the wire broke going to my input here? Well, right now it's normally open. A broke wire is normally open, which means I would not be able to stop my motor. So anytime we see a stop button, we're supposed to use an examine if closed, because the stop button is true when it is closed. So what I'm going to do is I'm going to come up here, I'm going to go offline. What can we do offline? Yeah. And I'm going to come up here and I'm going to click on this. Let's see if I can remember how to do this. And then I can come over here, so I'm going to right click on it, and I'm going to choose change instruction type. You'll see that listed. And then I can come up here and I can type X, I, C. And it automatically changes over for me. Yeah. So we changed it from an examine if open to an examine if closed. Yeah, XIC. You have to type it in. Now, after a while, we'll show you all this, but the whole palette of instruction is right here. So this is the palette. Everything that's grayed out, we don't have. Right up here. Let's see, let me close it out. Right here. So, okay, see where I'm at? So literally, you could change this to you could change that normally open. If you knew this palette, you could change that instruction to input. You could change it to a timer, you could change it to a counter. All we did was change it to a normally, to an examine if open to an examine if closed. So when you're doing your labs, anytime you see something labeled stop, you want it to be a what? You want it to be an examine if closed. So now I'm going to download it again. It's going to ask me, do I want to give it a revision number? And then I'm going to make my switch. So to make it normally closed, we just turn it over and it wants me to go online. We turn it to the right and notice the switch stays to the right. So that's the way we're going to simulate a normally closed switch. I'll wire the circuit up, by the way, when y'all go on break. I'll actually wire it up to a motor and show y'all what happens if I use that other one. So all you have to do on switch one, that is supposed to be it's supposed to be a momentary contact switch, is just take push button 1 or switch 1 and just click it to the right and let it go. And it seals itself in. So this is called a sealing circuit. So my motor would be running right now. If I connect it to the output, you should see output 0. You should be an LED on output 0 comes on and stays on, right? Because it's sealed in. You'll see that. And how long is it going to run? Until I take my stop button, just momentarily. So that's our first program. Examine it open. And this is an examine it closed. So notice it's true because I'm using a normally open push button. So it's a normally open push button. I'm using an examine if open instruction. So I'm going to come over here and this is my start button. Oh, I'm showing you the program. Okay, I'm sorry, I don't understand what you're saying. So this is my start button. I'm using 2 normally open. This is my start button. I'm going to press it, and it starts. So I've got that motor hooked up to that output. So even though that coil in there is not real, it's a program coil. If I assign it to that output, when that thing goes through, that output comes up. And this is my stop button. It's a normally open stop button because I'm saying it's true if it's open. So I'm going to start this thing up. And oh my goodness, I have a broke wire on my stop button. Can't stop my motor. I just killed all my workers. Because I have no way of stopping the motor. Wires break in the industry all the time. So for wire breaks, what would you like this motor to do? Stop. And then you can fix the wire, right? Right now I got a motor running and I'm trying to figure out what's going on. I'm trying to troubleshoot this sucker. So what I'm going to do is I'm going to come over here and take this. I'm going to hook my wire back up first so I can stop it. And then this is a normally stuck, the one without the button on it. This is a normally closed. I'm going to come over here and move it. So this is my common. So I got my common. This is my common. It's running over to the plus because I'm running syncing inputs. That means I'm running syncing inputs on my PLC. So that means my input devices have got a source, right? You understand? So I'm running the plus over to the common. And then this is my switch that's running over to them. Of course, now when I look at my program, my stop button is false. So I'm going to come up here and take it offline. And I'm going to change it over to an examinative close. Hit instruction type. Type in the 3-digit, right, examinative close. And it changes it. Check my errors. I got no syntax errors. And then I can download it. So what did I have to do to change the program? I had to go offline. Somebody on here is going to try to do it online. Who's going to do that? Dennis. Somebody is, I guarantee you. This thing won't let me change my program. And I'll say what? Go offline. Okay, so now I'm using a normally closed push button, and it says it's true. Can y'all see it? It's green, so it's true. Because I'm using an examinative closed instruction, and it's a normally closed push button. So I can start my motor. It runs. I can stop it. Here it is running. My wire breaks, and the motor stops. So that's the big difference between motor controls and programmable controllers. When we're dealing with inputs, that is not a normally open or normally closed contact. One of them is that it's true if it's open. The other one is true if it's closed. So this is, it's true if it's closed, right? And the other one is true when it's what? When it's open. That's what the examinative open and examinative closed. So, if you run into a diagram in the book and it calls that thing a stop, then you need to use an examinative closed instruction. Now, when I come up here and assign this a contact to this guy, then that's going to be normally open, normally closed. This examinative open and examinative closed only deals with inputting from the outside world. So on the input from the outside world, that is not a normally open contact, even though your boss might call it. They've been doing it for years and they understand the difference. That is an examinative close instruction. So I want this to be true when it closes, even though I'm touching it, and I want this to be true when I open it, right? You understand that? So I want it to be false when I open it, when I press the button. So I said that wrong. And that one thing right there gets people that has motor controls. They've had motor controls, it screws them up. Because in motor controls, we use a normally closed push button, and that's the symbol we use for a normally closed contact. Okay. So remember that. So I will correct you on it. And OSHA even says that you should always use an examine if closed instruction, right, for a stop button. But what's really neat is when I buy sensors, all my sensors can have normally open contact. And if I wanted to act like a normally closed contact, I would use the examine if closed instruction. And that's what's cool about a PLC. So now I don't have to have all these contacts, okay, I need that sensor to act like a normally closed, but all it gives me is a normally open. Well, good gracious, just call it what? An examine if what? An examine if open instruction. So it's really neat. So it's open, but in your circuit, it acts like a what? In your program, it acts like a closed contact. So that's our first program, guys. So what we're doing, I'm going to come over and show you this. This is my input table. And this is what the PLC actually reads. It reads these inputs. It don't read the input. The program reads the input table. So it scans, and it goes through a scan cycle. And this is why you don't want to reuse an output. And we'll show you, we do have so what happens if you put an output up here, and I'm going to demonstrate this, you don't get an error. Let's do that. So I'm going to come down here. I'm going to take it offline. Oops, I don't want to download it. I want to go offline. So what can we do offline? We can modify the program, or we can create a program, right? And what I'm going to do, I need to put another rung in here. What do I need to do? I'm going to highlight, and you can put the rung up here if you want to. I could put it above this. So wherever you insert that rung, it's going to go up above the one that you highlight. So I'm going to come there and highlight this one, and then I'm going to come up here and just click the rung, and sometimes it'll stick it in there for you. Okay. Then I'm going to come up here, and I'm just going to put a normally open push button. Normally open button. And then I'm going to come up here and put this coil out here. Okay. So I'm going to assign this to input : Everybody okay on that? I'm going to use a switch I hadn't used before. 0 / which one I hadn't used? I've used 0, 1. I'm going to use 2. Hit enter. Oh, I put a code in there. So it's going to try to take it as a symbol, so I can edit it because it hadn't been an address yet. Input : 0 / 2. Okay. Then we can call this anything we want to. And then I'm going to come up here, and I'm going to come up here, and I'm going to call this run. And I'm going to check syntax error, and it says, oh, got this in there by accident. So I'm going to check syntax error, and it says it's okay. But I'm reusing an output twice. So when this thing scans, it scans at the top, does this one, reads your input, runs the program, updates your output. Reads your input, updates, runs the program, updates the output. So what's going to happen, no matter what I do with this coil, since this guy here is scanned last, this is what that output's going to do. So I come over here, I'm going to download it. My output's not working. My output's not working. And I don't get any errors when I check it. Well, it's in the right syntax, right? You understand that. But I've messed up. So we're going to go online. And I'm going to come over here and hit my start button. It goes true. Well, my output's not working. Why is my output not working? Because this is the last rung scan. So it scans this one first, and whichever one it does last, that's when it updates the output. So it scans the rungs, inputs, outputs, and then, so what's happening is this guy here, the one at the bottom, has higher priority than the one at the top. So I'm going to come over here and close switch 2. right? Notice this one went true. Well, I can come over here all day long and hit the stop button, and nothing happens because this one has a higher rung number than that rung number, but it's in the right syntax. So so if you've got an output that does not respond, odds are you've done what? You've duplicated that output, that address somewhere in your program. So we used to do this on purpose, but what we would do, this was back in the days when PLCs were real slow. Now they update real fast. You know, I don't know if y'all was in on any of the old computers that were really slow. They only ran one app. They couldn't multitask for one thing. And what would happen is that every once in a while the PLC would miss an input. So what we would do is we would duplicate the rungs. So the rungs would be exactly the same. You can get by with that when we don't do that. So the rule is don't use the output or don't use the same output more than what? One. We could, but this happens all the time. So somebody in this class, every time I talk to this class, somebody's duplicated an output. So like you get up here and you what's output is free, and you say okay, 3's free, but you forgot you did what? You used 3, and then you come up here and then it don't work up here. My light's not coming on. I can see my input's going true, but that light's not coming. It's not energized. What happens is the rung down here is telling it to do what? To be energized. So the lowest rung has basically the highest priority, the one that's closest to the end. So this is one reason right here that we normally don't duplicate addresses. There is one exception. We're going to get into these two instructions called latch and unlatch. We'll get into those later. Those use the same address, and we'll talk about one. So normally, and I should rephrase, what did I say on that road? So I can't stop it. Well, I can stop it, but I got to stop it with what? So what I've done is I've come over here and I've done this. So what I've done is, so my inputs of my PLC are syncing. So what I've done on my inputs is I've carried my plus over. So my common. So what I've done is I've got my minus pointing towards my common on your input. And then what I've done is I've run the plus down. And that's this yellow wire right here. So here's the plus. Okay. And it's running over to my input. So here's the plus, this big red thing. It's running over to my input. Here's my input. And then I got a jumper that jumps over to the other input. So this is my normally closed. I could move it over to this normally open. So what I would do if I was going to use all these inputs is I would take the plus and jump it to all of them. And we just have red and black. You could use the reds as common and use these are nothing but push buttons. And use the black as the actual switch. And then the actual switch itself, here it is. So I've got it running over to my input right here. So this black thing, this is input. Now, if you're going to use these, you got to set all your switches to the center. And that way they're all turned off. And in that way, these are what's actually controlled. These are actually what's controlled. So this is running from that switch over to input 0. This is running from the switch over to input 1. So that's the way I've got it wired, right? So I've got this one. So PLCs are not hard to wire once you figure out the scheme of things. So I've got a normally closed push button, which is supposed to be a stop, so that's my stop. And here we're supposed to use the actual symbol, the electrical symbol. And then I've got this running into input 0, / 0, and then I've got the normally open running into input 0/1. Now on your switches, that they're just labeled 0, 1, 2, 3, 4, 5, like that. Now my outputs, so we got a program in here. On my outputs, here's my common. Here I have the plus pointing, so our outputs are sourcing. So when I hook up my motor, I hook it up like this. And I'm hooking this up to output 0/0. So when that output turns on, then whatever you have connected, but up here it's not a real coil, it's programmed, right? You understand that? But when that coil goes true, that output turns on, or that coil symbol goes true, the output. So this is the way I have these guys here wired up. And what we'll probably let y'all do is when your circuit, once y'all get on into them, we'll let you use this box right here and actually wire up the output. We're not going, but it would be just like I hooked it up here. So I could take this common here, I could run it down to here, and then I could take this wire right here, I could take a wire and run it up to there. So what's nice about this trainer is you can wire a PLC without actually wiring the PLC, using banana plugs, which makes it real convenient. Programming ladder logic, examine if open, examine if closed. Y'all okay on those instructions? That only deals when you're dealing with these input ports over here. When you're dealing with just contacts, they're just contacts. So if I had this guy right here controlling a contact and another rung, it's just a contact, and it will be that would be a normally open, normally closed. So those terms only deal when you're dealing with the input. And then we showed y'all RS links, right? So RS links is where we install the driver for whatever communication standard we're using. And they support a lot of them. We're going to look at Ethernet. We'll play around with Ethernet, but then once we establish this, the first thing we do is we select the CPU. And what's our CPU? Micrologic 700 Series B. But where can you find that information on just about every PLC on the right hand side, right? But as soon as you pull that cover off there to put another module on there, you lose that, so you need to keep up with that. In fact, the Siemens, this one, the cover comes off. The Siemens, it puts it on there, you just can't see it anymore. So if you don't write that down, see slot 0. We talked about syncing and sourcing, right? You understand? This is the way. So the lab book is set up. The lab book, I don't know if I've got the way the lab book is set up, but you're going to have to modify, when it says draw the connection, you're going to have to modify that lab book for your PLC. So it's set up for see if I got it here. It's set up for a SLC 500 that's got 120 volt input, which I've never seen, but I'm sure they're out there because 120 volts for years was the standard supply. I'm trying to see if I got the. So I'll draw the way the lab book is set up. So I don't have it in here. But what you're going to do is you're going to mark out what they have. So what they have on the book is not the way our PLCs are wired up. So, the book's I think the lab book's got 120 volts up here. Got 120 volts up here. First thing you're going to do is mark that out, because ours don't work that way. This is in your lab book, and you're going to change it over to what? Common, right? So this will be up here. If you look at your PLC, it says DC common. Okay. Then what do we have running up there? Well, we're running syncing input. So I've got the negative supply of the trainer running up here. So if you took your meter and went from here, the common, down to plus, it would measure 24 volts with the plus on the red. Then what we're going to do, the way our PLC hooks up, is everything we hook up hooks up here. Whether we're doing a push button or whether we're doing a sensor or whether we're doing limit switches or whatever, it's going to hook up here. So you're going to have to mark this out, and over here, it's going to have, I don't remember what it has. It's got common coming out of the port, but it don't. The common, so we're running sourcing output. So you're going to mark that out, and you're going to come over here, and then our output, and you might have to swing this up a little bit, guys. In the lab book, it's in there, I guarantee you. Oops. So we're running sourcing output, so that means we're going to mark out whatever that is, and we're going to put the plus toward this. I'm going to draw this thing small if I go up, and then our outputs are going to connect here. So when you draw the connection to the PLC, so the only symbols right now we've got in the program is we got examine if open, examine if closed, and a coil. And a coil. Right? The symbol for a coil. And we'll look at later on where the coil don't even have to generate an output. We'll look at our bit files as we go along. So sometimes a decision in your PLC program does not have to generate an output. It's inside your control. In motor controls, you'll learn those as control relays. So a control relay is a relay that the contact does not control power to anything. It's just in there for decision making, for logic, like ands, ors, nots, nors, and stuff like that. We'll learn how to hook contacts up there. So if I was going to use a relay, then I would have to use the symbol out here, a symbol for a true relay. If I was going to have to use a solenoid, then I would use a true symbol for a solenoid. If I was going to connect a light bulb, then out here I would use the symbol for a light bulb. But when I wanted to turn that light bulb on, then I'd say output, right? And then I'd put 0/2. And then when that symbol inside my program went true, I've got that light bulb hooked up to that output, and that light bulb will come on. So are these in parallel? Well, no, they're not in parallel, because if they're in parallel, both sides would be connected together. I see students do that all the time. They'll come in, they'll see 5 resistors, or just let's say 1 resistor, and they're connected on this side, and this side's not connected, and I'll say, are they in parallel? They say, oh, they're in parallel. But to be in parallel, both sides have to be connected together, right? We hook up this circuit right here. It's a rectifier circuit to turn AC into DC, and we'll come over here and connect these together. And then this goes to one side of the transformer, that goes to the other, and I'll go over there and look, and they'll have the diodes. Somebody in the class will have the diodes connected like this. They'll have them in parallel. But if it were in parallel, what? This side would be connected to that side, so we only got one side. So somebody's going to do that in the class. In fact, I'm not going to. I taught solid state last semester, and I had to go away for a training thing. When I come back, a guy had a lab signed off, and the instructor that covered for me You know, when I went over there, they had those dials hooked to parallel. You know, I'm telling you, it was incredible. So let's see what else. I think we're about through, guys. I don't know. That should cover everything that's on the test. Scan, so we need to understand that. So this is basically a scan. So here's our instructions we looked at so far. We looked at examine if open, examine if closed. Everybody okay there? This is structure, the one we've been using is called an OPE, which is an output enable. We have what we're going to look at. We have output latch. And this is used all over the time. It saves a lot of logic to go on. So this is the only time that you can duplicate a coil, is if you're using a latch and unlatch. So what I'm going to do is I'm going to go offline. So y'all understand why normally we don't do what? We don't duplicate coils because the first one is going to be ignored, and the last one, the one furthest down, is the one that's going to override the other.
That's one question right there. We got another ad right there.
I just gave that a name. I just gave it a name I wanted to give.
Okay.
Symbols are yours. Symbols are yours. And what you want to do though is you want to give it a name that gives you some idea of what it does in the program. So this stop and start is obvious, you know. I mean that's it. But when you do that, when we come over here, and I'll show y'all I'll show y'all the Allen Bradley diagrams, ladder logic for the Festo line down there, and you'll see every one of those symbols gives you an idea of what that thing does in that program. Yeah. And if you want to clarify it more, you give it a comment. So I think I showed y'all that. They put comments on everything. And why? Because you have programs that's out there for years, and then sooner or later, they're going to want you to modify that program. And you don't want to go out there and try to figure out how you did what you did, right? What you need to do is put something in there that says why you did what you did. And then that makes modifying the program a lot faster. Very seldom do you have programs that never, ever change. So they might change the style sensor. And if they change the style sensor, then you might be able to go from examine if open to examine if closed, right? You understand? Just because they have a different style sensor. Or they add a new section. And in between here, so you got this section over here and this section over here, now you got to develop programs in the center. So it's very seldom do you do that. I'm not going to say. So programs are modified often, although I do know some of it. So I'm going to go offline, even though this has an error in it, right? And I'm going to create a new program. So we can create a new program here. So I can come up here. I can use file, or I can go here. It says, do I want to save this processor? I'm going to say yes. And so I created a new program. And then what's our PLC? Yeah, Series B, right? And then what I'm going to do is I'm going to come up here and I'm just put a contact. Okay. You can't put anything in the end run, by the way. So watch what happens. They won't let you put anything. So I'll have to insert a run. And by the way, once you get it going, if you want 2 runs, you can just keep hitting this and it should. No, it didn't. Sometimes it goes over and just keeps going. Okay. So what I'm going to do is I'm going to put a normally open. And these 2 should be in your most used. I'm going to do a L for latch. So this is output latch. And then I'm going to do a U for unlatch. Yeah, I'll start a new one. So y'all can try to do it if y'all want to. It's okay. Y'all are master programmers now, right? Click on this one. I'm going to assign it to input. I'm going to go back to my switches, guys. I'm going to power this up. I'm gonna, cause I'd have to rewire two normally open. So I'm gonna come up here and I'm gonna call this input 0/0. This is a whole new program so I can reuse those switches again. And we'll call this, latch. And then I'm gonna come and assign this to input 0/1. And then, oops, that's what I did. I used the O instead of a 0. Somebody here is gonna do that, brother. 0/1. I'm the first one. And we'll call this unlatch. And over here, I'm going to assign this to output 0/0. And I'm going to assign this, and I didn't give it let's give this a symbol. So I didn't give it a symbol, so I can come in here, since I didn't give it a symbol, I can come up here, right click and hit edit symbol. So I'm going to come up here and I'm going to, by the way, once you start typing, notice your symbols automatically pop up. You just interested. So I will use this director, so I just type in an L, and I can stop typing, I can just come up here and click on that, double click on that, and it'll come up here and fill that information.
What do you have of that?
I have it, what do you mean?
It's 0.0.
Which output? 0/0. On both of them. So this is when we duplicate, this is the only time that duplicating coils is allowed. So we check it for errors, it says it's okay, but right? We okay? You okay? No, you never, that'll give you all, so don't do that in lab. Always start a new program. Because now you've got all these symbols assigned. And over here they want to call it Libet Switch 1, and you're trying to assign it, and they say, well, this thing won't take my symbol. Why? So if you try to enter a symbol and it will not take it, what do you think that means? Yeah, you've used it before. Okay. So don't take a program that you're working on and try to modify it, because I might come back and want to look at your other program for not one thing. Well, I overlooked that thing. Well, let's don't do that. And we got a syntax, by the way, on how you're supposed to give these files names. And then at the end of the semester, if you don't save them on the thumb drive, then we're going to have to wipe them out at the end of the term. I mean, you can call this Fred. Yeah, the symbols are for you, but I'm giving. Normally, we give symbols names.
The input. That's what I'm trying to remember you did in my head. I typed in that I hit enter, and then I put in the I.
No, you don't hit enter. You enter the address before you enter it. Before you hit enter.
I put all that in at one time.
You don't put the symbol in, you put the address in, and then you assign in a symbol. So think about the way you do your phone. When you put in a contact, what do you put in first? The phone number. So what we're going to do is we're going to put in the address first. And then you hit enter. And then you put in the contact area. You put whatever name you want to know that by, So that's exactly the same thing. So enter your address first, and then when you hit enter the name that you want to call that. Just like you do on your contact list on your phone. And what's so nice is that once you've got a name out there, then you don't have to know the number anymore. I think I told you, I had a guy call me and wanted to know my son's phone number. And what I did, I didn't have my phone with me. I said, I don't know it. He says, I can't believe that. I can't believe you don't know your son's number. I said, I got him in a contact list. So my Cherokee, you can actually tell, You can call through I guess some of y'all might have that. So you can call through the display, and that's what you do. You just say call Peggy, which is my wife. I guess I should call wife. And it'll automatically dial for me. But it's probably because I gave it a what now. I gave it a name. I don't know if you can call out a number or not. I need to figure that out, right? So we got it. We got it. We got it. We got it. You got it. So this is just practice. And the first program in the lab book, they're going to give you they're going to give you the program, and you basically got to enter it in. And then later on, they're going to start just saying, okay, we want to do this. And then it's going to be up to you to figure out how to put the program together to make it do what it wants to do. Especially in PLC2, or IFC 196, they don't give you any of the programs. They give you what the program's supposed to do. So even though it's written around RS Logic 500, we can still do the lab, but we'll just switch over to 5000 because it's not giving you the program, it's just giving you what the program wants to do. So we'll do all that, you know. And so we'll look at the difference, and you'll be surprised how similar it is to this. The addressing of your inputs and outputs are a little different, but it's not really hard. In fact, with that one, you can choose the address from a menu, which is really neat. So whether you got it or not, I'm gonna go ahead and upload this so y'all can see why we can duplicate outputs for this instruction, for these two instructions. So when you do a latch and an unlatch, the associated latch they will have the same address, and this is what it's reading. In fact, I've got it in there somewhere. I'm just gonna. I've had that pro. By the way, when you start typing them in, if it's in there, it'll pop up. And like I said, that's another big difference between the newer programming software and RS Logic 500. RS Logic 500 does not ask for a name until you either save it or you download it. All your new applications, as soon as you say you want to create a new, they don't call them program. Project. The first thing it's going to ask you for is what? Is a name. Which is usually what's true when you create files anyway. Okay, so we got it in run. So so we got a momentary contact if we go to the right. So I'm going to do 0 and see both of them went true because it's what? It's latched. And it's going to stay latched from now to ever until I do what? Unlatch it. So this is one of the Allen Bradley programs. They do that a lot. So PLC 3. Programming. So this is the actual program that runs the first module. No, that's not it. Distribution. Oh, PLC program. There it is here. This distribution, here's the program. So we'll talk about this later on, but let me get into the section called auto. Can you see what they're doing? So this is the way they set up a sequence. So here they latch this output, they unlatch that one, they latch this one, and that's basically the way they're going through the sequence. So they just so they want to make the robot go from this side to that side. Well, here you would latch it, and you want it when it comes over here, you want it to automatically go back. So you hit over here, and then you'd unlatch it, right? You understand that? So you see these latch and unlatch. Siemens called them set and reset. A latch and unlatch just saves us a lot of time. We latch it, and then we can go down, and sooner or later we're going to do what? We're going to unlatch it. So this is the only time that you are allowed to duplicate addresses without getting in trouble. So this is true. So I don't know how that rule is set up. It should be. This does not apply to latch and unlatch. So we duplicate the addresses for the outputs. We latch the output, and how long does it stay latched? Till you unlatch. One shots, we're not going to look at those. We will play. We don't get that. So this is the scan, and you can understand why this run, before it updates the outputs, it gets down to the bottom, updates the output. So whichever runs down at the bottom basically has the highest priority. And by the way, we call it a scan time. So we can actually look on RS Logic 500, if I can remember where. Yeah, so this basically tells me the scan time. So to run this whole little program I've got, it's taking 5 microseconds. I'm sorry, 500 microseconds. And of course, the ultimate goal of a programmer is to make the scan time as what? Small as possible, right? What else do they talk about? 10 times. Okay, program calls. So we call this on the left, it's called the project tree. Y'all can see it on yours. And then we have some data files over here that are dedicated. So we have, this is the actual controller. So this is where you can go and I could rechange the communication method. So if I set my communication up for Ethernet IP, I could change it over to this if I want. We can give the CPU a name. So, and right now, every time you save, it says the CPU is what? Untitled. Well, you could give it a name. This is where these are system files. I don't even know why they show them. You have no access to those whatsoever. Oh, by the way, we can also look at the status. If you get an error that pops up, and that's going to happen here because y'all are new to this and y'all don't know everything. But we can come up here, if you get an error, then we can come up here and actually look at the processor status. And this will actually, can y'all see this right here? In the PLC2, we'll show you how, this is called a free running clock. It's really cool. And we can actually use that. So this would be where we would go to look at errors. Sometimes it'll give you a number, and then you'll have to look it up in a book that tells you the best thing to do. Also, you can come up here and the arrows will always pop up here somewhere. And one of the options, if you get an error, right in here on the run, there should be another option that says clear errors. So try that first, right? And see if it'll clear out. And so we're in running now, so let's go offline. So controller properties, here's where you can come back and give your processor name. So now every time I save a program, is going to be what? It's going to be processor rich. So this way, what you can do, if you got a bunch of PLCs networked together, you can give every one of the PLCs a different name. And then when you bring up that communication thing and you select a PLC, then you're selecting it by name, right? You understand? So you might give it a name on what it's running for. This is where we can actually go and change the CPU. So I could pull this program up, and it's got 1100. It might be able to recompile it for MicroLogic 1000. We can assign. Don't do this. You'll see this. Don't do this. We can assign this a password, which means if you assign it a password, nobody else can deal with this unless they know the what? The password. Just like these computers. Processor status, this is what we'll look at if we're having problems. Scan times. Function files, we're not going to deal with that. IO configuration. So this would be if I add a module. Once I tell it it's 1100 PLC, it has no idea. So if I had modules over here on the right hand side, before I did anything, I would come over here and I would find the part number for the module and I would stick that on there. So this is what we talk about configure the IO, which would be the second thing you do. System files, ladder 2, this is the program. By default, it's called ladder 2. You can come up here if you want to, and you can rename it to Fred. Sorry. So, I know I got an error there, guys. I don't know what I did. Okay. So, where we're at, so I could right click on it, choose what? Rename. And you can call it Fred. It's still going to be file 2. So you can change these tags over to whatever you want to. I can still Fred. And notice down here on the tag, it changed to what? Fred. So by default, it's ladder 2. That's file 2. But you can give it a name if you want to. So that really comes in important when we start dealing with in PLC 2. When we start dealing with subroutines. Most real big programs, it gets very, very cumbersome to work with those. So what they'll do is they'll take that program and split it up into individual modules we call subroutines. And in that way, now instead of me we might have one subroutine that does this and one subroutine that does that. And now instead of me trying to figure out where it's at in 100 lines of code, I can just go to the subroutine that takes care of that thing. So we can do that. So what we can do here is I can right click on this and say new, and then automatically it's going to give it file 3, and I can call it like a subroutine, and I hit up, and then what happens is now we get another tab down here where we write the subroutine inside there. I'm going to delete that, by the way. So I want to get rid of it. Right? Not Fred. These are different data files. So outputs are actually data file 0. We don't have to specify it's 0 because they're internal. That makes sense? Your inputs are data file 1. You have by default, you have 256 words of memory assigned to input. And each input is 1 bit, right? So if you want to say, well, how many inputs could I have with 256 words? That would be 16 times 256. I don't think you would ever run into an application where you needed more. Status, we'll use these. This is the same thing that's up there, by the way. And then, of course, binary files, B3, we're going to start using these. The problem is if I have a coil that does not require an output, because we've only got 6 outputs on this PLC. But I've got a coil that does not need to generate an output, then we'll use these B3 files, and we'll get into those later on. Of course, timers, what do you think? T4. file 4. These are going to be for timers. So later on we'll get into timers. Here there's a lot more memory because each timer requires 3 words. And we can put 256 in there. Now it doesn't mean you can put that many, that's how many is available, but the PLC's got so much memory in it. I think this right here's got 16K. Is that a lot for a PLC? Pretty good deal because it's all binary. So what eats up memory, guys, is this garbage right here. This video stuff. This eats up memory. So as soon as we started to go into these graphical user interfaces on all these applications, our applications started to get used. So when IBM PC first came out, you could put 600, the maximum memory you could put in that thing was 640K worth of RAM. Was that enough? Sure, we was using a programming language called BASIC, which had no graphics at all, which is pretty neat. So yeah, we wrote pretty good sized programs. So what has killed us? And why does our phones have to have 16 gigabytes worth of memory in it? For the what? For all his graphics. Good gracious, you'd be surprised how much that eats up. So we have most of the internet, they're running an operating system called Unix. It's a text-based operating system because they don't need what? They don't need graphics. Okay, so project 3, everybody okay there? System files, we can't do anything with system files. To me, I don't even know why they display it in the project 3. Seems to me, if the operator or the user can't get into something, why put it up there? So most of your UPLCs don't. Okay, this is talking a little bit about subroutines, right? So these extra subroutines. So when we take a big program and we split it into modules, this is called structured programming, by the way. And if you ever worked on a ladder diagram that's like 200 lines of code, and you're trying to figure out what part of that does that, what rung it does it, you'd cuss them people out in a heartbeat because you write structured programs. So what would you do? So back there on that robot, anybody that has robots, that robot does several tasks, and it's all written in subroutines. So when we came over here, when the robot was over here, they taught the points, and when they moved the robot over there, it missed the points. So instead of me trying to find it, I would find the subroutine where it picked up the block, and I would teach that point. And so instead of me trying to find the section of that program that taught it how to pick the block up, I just found the subroutine that does that. So I was able to teach, and I could loop those subroutines, and I could reteach the points until everything was right. So writing structured programs is something that you really, really need to learn. We won't deal a lot with subroutines in this class because we don't have a lot of time, but we will get into subroutines if you take IoT 196, which is offered in T2. So I'm pushing that course, guys. Floating point, I think this is not in your book. Inputs, outputs, status, timers we're going to deal with. Control counters we're going to deal with. We're not going to deal with the control register. It's deal with some high-level instructions. Well, we will talk about integers. We won't play around with the integer. We won't play around with the integer register. But the floating point, the book doesn't talk about that. F8. Bit files, we're going to be able to use this thing for all time. We're going to use it for internal calls in this class. When we get into PLC2, we use it for shifts and all kind of stuff. There is another one that this guy right here supports. It's called a long L file, which lets us deal with 32-bit numbers. So we'll show y'all that too. How you can add more program files to that. Okay, we talked about this, right? Examine off. Anybody got any problems with examine if open and examine if closed? So got that down? These symbols should be caught. So we only need to really know this when we're dealing with input devices, when do we use an examine if open and when do you do an examine if closed? If it's a contact inside the program that's being controlled by a program coil, then we don't have to worry about it. That makes sense. Find my program. So this is an examine if closed. That means I've got to close the switch for it to be true. But if I was, am I offline? Yeah. But if I was to come down here and I wanted to come down here and I was going to come over here and pull down the contact, and I'm going to call it latch, unlatch. So now this contact is being controlled by this coil. If this coil goes true, this contact closes. So that means it would be considered a normally open contact. But that is not an input. That is a simulated contact that's being written inside the program. If we don't want to so I'd have to have some type of output over here, guys. And we'll output 0/, which one's 1. Okay, and I'm not going to give it a symbol. If I say, okay, so I just sacrificed, so right now I'm using 2 of my outputs. I'm going to come over here and put another rung. Okay. And I'll put just coil. And I'm going to come over here and I'm going to put a coil. And we can call this input colon 0. Let's see which one I had to use. 0/2. And over here, I'm going to say B3 colon 0/0. So that's coil. But it doesn't use one of my outputs. So we call these internal coils. So you've only got 6 outputs, and I've seen people do this. They'll use an output, and they say, well, I don't have any more outputs. Because they assigned an output to a coil that doesn't need to generate an output, right? You understand that? So these are what we call internal coils. Every PLC's got them. They give you the ability to use a coil to make a decision inside your circuit, but it don't need to turn on a light. It don't need to turn on a motor. It don't need to energize a solenoid. It don't need to do that. It's going to be just in there to make a decision. And we call these internal coils. So that's one use of your B3 files right there. You got a ton of them. You got 256 words worth of bit files you can use, as long as you got enough memory in there, in your PLC. So it seems like we got a lot, but it's all, and by the way, you can create, if this isn't enough, we can come up to data files, and I can come and say new, and then I say I'm going to create another binary file, which is B file, and I can give it a name. So in this PLC, we can create we can create additional data files, any one of them they want. Okay, we'll try that. So now I got a B9 file, which I'm calling 2. So now I got 256 more 16-bit internal coils I could use. So we can create more timer files. So when you click on this and you say new, it's going to ask you what type you need. So you can come down here and create another timer file. You can create another counter, and there's more in there we're not going to talk about. Is my program still good? Yeah. So I think that's it for this chapter. So we got a good look at. So this is the syntax. This is important. So this is the syntax of an address. So we start off with a data file. In, out, B, timers, counters, etc. Then we put a data file number. Now, on your inputs and your outputs, those are understood. So we don't have to put 0 after output. You can, but it'll just go away. And we don't have to put 1 after input. But your timer, like it's T4, so you gotta say T4. Because you can have multiple T4 data files. So I can add another timer, but it might be T9, right? You understand that? So you gotta specify the number. The only time the number is not required is when you deal with true inputs and true outputs. Slot number is required. What slot are we using right now? 0. If you have multiple words, or if you're going to identify a whole word, you put a dot, then you put the word address. If you're not identifying a word, then you just look that up. You put a what? If you're specifying a whole word, the note 3 says bit addresses are not required when you're addressing an entire word. That's supposed to be word. That's not word. So I got 2 problems, right? Bit addresses are not required when addressing an entire word, not word. So this is the actual. This is not in your book. This is right out of the book, that the actual book that goes with the field tree. And we'll be referencing that every once in a while too. Like I said, the guy is really good on the book, but he does have some problems. He misuses the word register. He'll draw a normally closed contact hooked up to the PLC, and then he'll use an examine if open instruction inside his program. That's one of the problems he has. Like I said, he calls elements, he calls them registers, and we'll make sure y'all understand that. So this is the actual syntax. So I need to correct this. I can't do it right now. Bit address is not required when addressing the entire word. Yeah, I see that. Thank you. So data file numbers are not used for your examine if closed, examine if open, for normally closed, normally open, or output enable instructions, or even latch instructions. So status register shows the flags. I showed you that, right? Flags are things, this came up from, we call them flag registers, and we'll refer to that. So what happens is these status flags, they sit there and they're looking at what they're seeing, what's wrong. And if something goes wrong, they just basically raise their hand. So they'll have a 1 in there. So if we go back and look, right now, what we'd like to see when I look at that status register, of course, mine's not in run, but when we look at the status register, we would like over here in errors to be all 0. So, but all it's going to be is a 1 or a 0, right? So if I have an override or a startup protection fault, or if I had a major error fault, then that 0 is going to be a 1. And then we'd look up, and if I don't clear it, so if you get a fault up here in this drop down, one of your options is going to be clear fault. If it don't clear, then we need, sometimes we can drop out of the application and reload it back up. But if we don't, we'll have to go in and we'll have to look at the error list and see exactly what that does, what we need to do to clear it. And we do have those available. Of course, we've been okay so far. So what else is status? It's going to give us the free running clock. It's going to tell us the scan time. And that's how long it takes to run the entire program, right? You understand that? It's going to tell us if we have problems with math. We're not going to get into math this time. If we have overflows or underflows or carries or anything like that. Debug protection. And we're going to look at forcing later on too. So that's one of our labs. We'll lecture on forcing, which is inside the status register. Let's see. Processor, that's just catalog, scan time is important. Math, we won't need that until we get into PLC2. Let's see, chain, we don't need that. Errors, protection, memory modes, and force. We'll look at force. Force later on, that's a whole section on that. What is the timer T4? We'll get into timers toward the end of the term. We'll have we have three types of timers we'll look at. Counters, those will be so timers and the counters will be the last thing we'll go over in this class. Control registers, we're not going to look at that. Integers, we'll talk a little bit about that, especially the range. So integers are signed numbers without fractions, right? We can represent 32,767 minus 32,768. And we'll explain why we have one more negative number than the positive number. The 1100 supports a long word, which is 32 bits, right? So if you set up a long word, then you can get 2,147,847 plus, and we can get one more minus. So y'all will find out why that's true. So odds are, if a company wants 32 bits, they're not going to have any problem. UPLC supports double long words, which is 64 bits. With 64 bits, I'd have to look that up too. I can't remember, but that's a lot. We can look at our. So where's my calculator at? Right here. So let me put it scientific to the 64th. And then I can divide that by 2. And that would give us our range of numbers. This would be negative. The positive would be one less. So 64 bits. I don't think a company would ever need more than 64 bits to represent numbers, would y'all? So that's a big number. And if you're a really good programmer, you could actually combine them. So this is long words. So the 1100 supports long words. It's not in the list, but what you would have to do if you wanted to use them on the Allen Bradley PLC or this PLC, you'd have to insert a new, and then you would come down here and say long, and then you'd have to give it a name. You could call it long. And now what we've done is we've added 64-bit numbers, integers to our scheme. The real numbers, these guys will use scientific notation. They will automatically, so they work like your calculator. Once you exceed a certain range on your calculator automatically switches into scientific notation. So floating point numbers are real numbers. We can get huge numbers. So we can get up to 3.48. So you can't see the listening. 3.4028 times 10 to the 38 positive, and then times a minus. So these guys, now as soon as you switch in, as soon as your PLC switches into scientific notation, then you lose accuracy, right? You understand? Your calculator range. So that's what that F register is for. So we're not going to use that this semester. But we would do it if I was going to do some high-level math, addition, and subtraction. And you can add more of these if you want to. And of course, the bit files, we call them B3. The book calls them B3 and B10. B3 is by default. And then on this one, if you want to add another B file, you could put it out. Anything above 8, you could give it that number. By default, it's going to automatically go to the next one. So we use this for a lot of things. We use it for internal coils. We're going to use it for some of our instructions, internal relay coils. Some of our, when you get into PLC, tuning, if you take that class, we'll look at bit shifts and sequencers. It's going to use the D3 file. So primarily this one, we're going to use it for internal coils. So these are the three modes we can put our PLC in. What do we got ours in? Well, if I had it in program mode, I could not upload a program.
I was saying it might be offline.
No, that's okay. That's the program. So our program basically has two modes. Our program has got, basically it's got three, but this does it automatically. It's got offline. That's where we write our program. It's got online, which that's where we can upload or download or upload our program. And then it's got what we call a monitor mode, which means that allows you to see the flow inside the program. Ours is switching automatically, right? You understand that between the three because we have our PLC in the remote mode. Your PLC has three modes. It's got program mode. What can we do in program mode? We only modify the program in my computer. I'm talking about the number of modes this guy right here has. So to modify the program, I've got to have my application in the offline mode. We got two modes here. We got offline. We got three. We got offline, online monitor. Online monitor is when those green line pops up there that shows me what's true and what's false, right? You understand? So that's the three modes we have here. The three modes we have here is we have program mode, we have run mode, and we have remote mode. Which one is ours in? Remote. What does remote do for us? Our application switches it between these three modes, between the two modes. Huh? Yeah, I know. I can tell.
I'm sorry, I was.
Now, if we wanted to, in this, this was the problem we had with his. I know it's time to go there. So up here on this panel, if y'all can see, I don't know, I'll try to put it where y'all can see it. I can hit escape, and one of my options now is I can go down here to mode, and I can switch it to program mode. Now, I cannot, this guy right here, I couldn't switch it manually. It would come up, what you're saying? It says the PLC's in run mode, right? You couldn't do anything with it. Okay. And I could come up here and switch this in offline. Now, a lot of your newer PLCs, there'll be a key in there where you can switch it to program, remote, or run. And what you'll see a lot of people do is they'll switch it to run, then they pull the switch out. So means another person can't come up now and do what? Hook up to the PLC and change the program because they don't have the key. So a lot of PLCs have a key that you switch them between the two. This one, we can do it here. So remote mode, I can switch it between run and program with my application. And that's what we got ours in. If I had it in program, it wouldn't let me do it until I came up here and went to mode, switched it to program, then I could upload it, and then do what? Then I could switch it back into run. So what we like to do is use the remote because that allows us to switch it between the other two modes with our application. And y'all saw it pop up, right? It says go, do you want to go online? Yes. Then it says, do you want to go online? Or I can't remember the third one, to actually see what's going on. So on the Siemens PLC, you have to switch it to monitor on their program, or you won't see the flow. Offline, online monitor. So that's the three modes that's available on these PLCs. Oh, this is the way the book, this is the way all your labs are set up. And this is all we need to talk about. So this is the way your lab book is set up. So it's got plus 120 volts up there. Do we have a plus 120 volts on ours? So what are you going to do on every one of them? Yeah, you're going to stretch this out. You're going to come over here and you're going to draw your power source. So we're running syncing input. You're going to draw this over here. And then over here, this is true, but they don't have a power source. And over here, you're going to, so this is the way our PLC is wired. It's running syncing input and sourcing output. So this is the way you'll modify yours. Everybody's going to do that for me, right? 120 volts, we'd be killing students left and right.